How efficiently a hydraulic system operates and how long various components last depends a great deal on the condition of the fluid in the system. Excessive heat, entrained air, and contamination can all affect the overall performance of the system. If the fluid gets too hot, it will lose viscosity and may not provide adequate lubrication. This can lead to increased wear, slow response, erratic operation, solenoid burnout, and early component failure. Air entering the system during operation can also cause serious problems. Air contains water vapor, and when the fluid is allowed to cool, the water condenses on metal surfaces. This can lead to rust, which eventually ends up in the fluid. The rust particles can clog orifices, interfere with lubrication, cause unreliable operation, and create maintenance problems. Rust is not the only source of contamination in a fluid. Dirt is often responsible for much of the damage to components in a hydraulic system. Dirt interferes with the transmission of hydraulic energy by plugging orifices, and it reduces the ability of hydraulic fluid to release heat. The most significant problem, however, is that dirt interferes with lubrication. In this lesson, we are going to focus on three components of a hydraulic system: reservoirs, coolers, and filters. We are going to examine how each of these components affect the condition of hydraulic fluid. We are also going to discuss some common sources of fluid contamination and what needs to be done to eliminate them. Let's begin with the reservoir. Often it's called the sump or tank. Basically, all reservoirs work the same way. Fluid enters the reservoir through return lines that extend below the surface of the fluid. This prevents splashing, which would add air bubbles to the system and could cause pseudo-cavitation. All return lines come in on one side of a reservoir baffle plate that prevents the fluid from being immediately drawn back into the pump. Instead, the returning fluid mixes with the other fluid in the tank. The large steel sides absorb heat, cooling the fluid. At the same time, entrained air escapes and a lot of contamination settles out. The reservoir's dished bottom collects the dirt, and an end cover permits occasional cleanout. A drain allows sampling of the fluid. A gauge indicates the fluid level. A filler cap includes a built-in breather to let air escape. A sturdy plate provides a place for mounting the pump and motor. Three kinds of reservoirs are commonly used. The most common, the conventional, has the motor and pump mounted on top. Two other designs that are becoming more popular are the overhead and the L-shaped. Both place the motor and pump beneath the reservoir so gravity can keep the pump full of fluid. Sometimes, when the tank is unable to dissipate all the heat produced by a system, coolers are used. Coolers are often required since even very efficient systems may convert much less than 80% of their energy into usable horsepower. The rest is heat. Two kinds of coolers are used: air coolers and water coolers. Air coolers work in much the same way as the radiator on a car. Hydraulic fluid is circulated through tubes which dissipate heat through fins. The fins are cooled by a fan. Water coolers operate a little differently. They circulate water through a bundle of tubes encased in a housing or shell. The hydraulic fluid cools as it flows over the tubes. Since coolers are normally not designed for operation at a pressure of more than 150 psi, they must be installed in a low-pressure part of the system, such as a return line. To prevent any damaging surges in pressure, a 65 psi check valve is often installed in parallel with the cooler. All hydraulic systems today require filtration to keep their fluid clean enough for satisfactory operation. Correct filtration and careful maintenance of the filters helps ensure proper lubrication, smooth operation of valves and pistons, and a system that runs efficiently and reliably. Hydraulic fluid must be extremely clean to assure proper operation. Virtually any dirt will cause problems. Very fine particles can build up inside clearances like silt in a stream, clogging valves. This is especially true if the valves are not cycled regularly. Medium-sized particles can work into clearances, break down lubrication, and cause excessive wear. Large particles may actually block openings, plugging up the system. Any dirt that mixes with hydraulic fluid makes a very effective grinding compound that will cause rapid wear. This is especially true in spots like this, where the vanes of a pump ride on the cam ring. Hydraulic fluid clean enough for modern hydraulic systems must have no particles larger than about 1/3 the diameter of a human hair. The end of this shaft of hair, which is about 70 microns or 70 millionths of a meter across, is 3 times as large as the acceptable size for particles in hydraulic fluid. In some systems, even that would be too big. That's pretty small. In fact, it's less than the smallest thing most people are able to see. That means you can't tell by looking whether hydraulic fluid is as clean as it should be. For example, this fluid is clean enough. This fluid is not. Determining whether a fluid is clean enough can be done only by counting the particles and their sizes, either with a microscope or with a special device called a particle counter. However, filters that are properly selected, installed, and maintained will keep a fluid clean enough for extended use. 2 kinds of filters are used. One kind, the depth filter, works a lot like a coffee filter. Depth filters depend upon layers of porous material or media, often treated paper. When hydraulic fluid passes through the filter, dirt gets stuck in the media. Since depth filters have no consistent hole or pore size, they are usually rated based on an average pore size. If the depth filter has a nominal rating of 40 microns, this means there are some holes larger than 40 microns and some holes smaller. When the filter is first installed, it will remove much of the dirt 40 microns or larger in size. However, some particles which are larger than 40 microns will still slip past. When comparing depth-type filters from different manufacturers, make sure both brands use the same basis for rating. Otherwise, the comparisons will mean very little. The second type of filter, the surface filter, works like a kitchen strainer. It's a wire mesh or perforated metal sheet through which the hydraulic fluid passes. Wire mesh is similar to the screen wire used on your screen door at home, except it's usually made of bronze or stainless steel. Perforated metal is simply a sheet of metal with holes punched through it. Surface filters have absolute ratings which indicate the diameter of the largest round particle which will pass through the filter. For example, a wire mesh surface filter with a 74 micron rating will have square openings that are 74 microns on a side. A perforated metal element will have round holes that are 74 microns in diameter. However, that does not mean that no particles larger than 74 microns will get through the filter. For example, if a sliver of metal happens to be 150 microns long but only 3 microns thick, it may shoot right through a surface filter without even touching it. To determine the kind of filter and the rating needed to protect the components of a system, you should check with the manufacturer of that component or with a reputable filter manufacturer. Filters remove dirt from a hydraulic fluid, but there's a lot you can do to keep dirt out of the system in the first place. Paper cups, cigarette butts, metal chips, emery paper, rust, paint, all of these have been found in the reservoirs of new systems, so all systems should be carefully cleaned out before they are used for the first time. Dirt will likely get in when the system is first installed, and more may get in when repairs that open up the system are made. If parts of the system are disassembled, they may be worked on at a dirty workbench, then wiped off with an old rag before being reinstalled. When new parts are added to the system, slivers of metal may also wind up in the reservoir. If hydraulic fluid is caught in a bucket until repairs can be made, the oil may be dumped back into the reservoir. Dirt will almost certainly be in the bucket, and it will contaminate the entire system. Another source of potential contamination is the breather cap. During normal operation, the system's reservoir heats up and cools down, pushing air out and pulling air back in again. Incoming air brings in water vapor, which condenses into water when it cools. This contaminates the fluid, lowers its viscosity, as well as promotes rust in the system. Dirt can also get into the system through worn wiper seals around cylinder rods. Cylinder rods in dirty locations will carry dirt into the system if the wiper seal doesn't get all the dirt off during each operation. Finally, adding new fluid may be a source of contamination. Clean buckets, hoses, funnels, pumps, even clean hands are a must. Even the fluid itself can be a problem. For example, new hydraulic fluid straight out of the drum has usually only been filtered down to about 50 to 70 microns. It may not have been filtered at all. If you have a system which requires, say, 25 micron filtration, then the fluid from the drum must be filtered before it goes into the system. You should make sure the transfer pump you use provides adequate filtration for the system. Otherwise, even brand new fluid can cause operational problems. Most hydraulic systems today filter all the fluid in the system, but a few still use proportional filtration. In this filtering system, only a portion of the pump's flow is bled off through a filter before being returned to the sump. Proportional filtration is generally not adequate for the narrow clearances of today's hydraulic systems. Instead, full flow filtration is used. The filters are generally placed in at least one of 4 locations. Many systems have a filter in the reservoir or sump where much of the dirt in a system eventually collects. These filters are called sump strainers. Usually they're relatively coarse filters, often 74 microns or larger. They're on the suction side, so they protect the pump by filtering the fluid before it goes through the pump. And they generally cost less than other filters. However, since sump strainers are below fluid level, they are hard to clean, especially if the fluid is hot. They also have no indicator to tell when they're dirty, so they can easily get dirty enough to starve the pump and cause cavitation before anyone notices their condition. Finally, sump filters do not protect the system from the contaminants generated by the pump. Suction line filters, like sump strainers, are also placed on the suction side of the pump, but outside the reservoir in front of the pump. The filter has a replaceable element which can be coarse or fine. Like the sump strainer, the suction filter protects the pump. However, since it's outside the reservoir, it's easy to clean or replace. And it can have an indicator to tell when the element is dirty. However, it too may starve the pump and cause cavitation if it's not sized, installed, and maintained properly. And like the sump strainer, it doesn't protect the system from contamination generated by the pump. A third kind of filter is the pressure filter. It is placed in the system on the pressure side of the pump, between the pump and the rest of the system, or at a valve. Pressure filters can provide very thorough filtration, often as small as 3 microns or less. This is because the full pressure of the system is available to force the fluid and the contamination into the filter. Pressure filters, like suction filters, are easily serviced, and most have an indicator to show when they are dirty. One disadvantage, however, is that they must be built to withstand high system pressures, so they are relatively expensive. Also, if pressure and velocities are too high, the filter element may collapse or tear. Return line filters clean dirt from the system before it has a chance to return to the sump. They are installed in the return line to the sump. These filters generally have a rating from 40 microns down to 3 microns or less. Although return line filters operate under some pressure, they aren't exposed to main system pressure, so they are less expensive than pressure filters. One disadvantage of a return filter is that it only catches the dirt after it has been through the system, not before. Proper maintenance of filters is critical to the operation of the system. As we said, dirty sump strainers can cause pumps to cavitate. As suction, pressure, and return line filters get dirty, the pressure differential between the filter's inlet and outlet gets larger and larger. A very dirty suction filter could cause the pump to cavitate. A pressure filter could rupture or collapse. A return line filter could create back pressure, which would interfere with the normal operation of other components in the system. To prevent this from happening, suction, pressure, and return line filters may include a bypass valve, usually a spring-loaded piston. The spring may be changed depending on what bypass pressure is desired. As the filter gets dirty, the pressure differential across the filter becomes larger. As the piston moves up, it compresses the spring. When the differential is great enough, the piston moves up far enough to allow all the fluid to bypass the filter. These filters will continue to bypass fluid until the element is cleaned or replaced. Filters usually have indicators which show at a glance whether the element is clean, dirty, bypassing, or missing. A filter should be cleaned or changed when its indicator says it is dirty. Filters allowed to bypass hydraulic fluid permit contaminants to build up. In this lesson, we have seen how reservoirs, coolers, and filters are used to keep hydraulic fluid in good condition. Keeping fluid cool, clean, and free of air will help the system run efficiently and reliably.